So, here are the answers. You know what? I forgot to plug in my big speaker. There we go. Hey, what are people who study objects in space?
Strong.
Okay. What's a general term for all the objects in space, including the sun, other stars, planets, and the moon? Keeping in mind that we've, if they'd said astronomy, which one do you think? Yeah. Celestial bodies. So kind of mark your own. What's energy that's transmitted in the form of waves? Yep. Radiation. Those three, meh. If I put a star next to it, that means I like this question, I like this question, I like this question. Why would I say that? Did you hear me say it's going to be on the test? You're just kind of the student that notices when a teacher tends to emphasize things. That's a good student. What are moving away from each other? What tells us that the universe is expanding? Galaxies. Aiden, you're on a roll. You're getting the candy if you keep going. Now, this next one you have to get from the textbook. And I am sometimes, I'm going to be letting or making you guys read your text a bit more. Have you figured out, by the way, and if you haven't, I need to show you this, you figured out the quick study trick for the textbook. If you're studying in a hurry, Riley, all you do is you go da 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 da. I mean, cool pictures. This is kind of interesting. Is that word in bold font? I probably need to know that. Is that word in bold font? I probably need to know that. Radiation, I probably need to know that. Oh, spectroscope. Separates the light. You know what? I think the answer that we get here is a spectroscope. Excuse me. This instrument first detected background radiation in the 1960s. Yep. Radio telescopes. Turns out, if you look at your notes, if you look at your textbook, background radiation has also been mapped by space probes. The term blank, you know what? What's used when wavelengths of a star become longer as they move away from you? This is how we know the universe is expanding. This is an important word. Yeah, redshift. Okay. By the way, if a star is moving towards you, and there are a few stars that are moving towards us, because things are moving all over the place, there are a few stars that are moving towards us, their wavelengths become compressed. What's the theory that suggests 13.7 billion years ago, a tiny volume of space suddenly and rapidly expanded to an immense size?
Big Bang Theory.
Mm-hmm. Well, let's be clear. The show is just like the theory. It was named after the theory. The theory was not named after the show.
Well, you never know that.
I do know that because it predates the show. Then you would turn the page. E. A. Redshift is when you're moving away. Radiation, G. Spectroscope, F. I'm I'm going to see if we can play with some spectroscopes. I only have about 6 that work, so I'm going to come in on the weekend and see if I can fix up more. It may just end up being that I only have 6, and I just let you look through them a little bit so you can see how they work, but we can't actually play with them. An astronomer, studies. D. Find this? Yeah, you do. Evidence indicates that galaxies are moving away from each other. Number 8, the Big Bang Theory. Well, it states that the universe began with an event. I'm not wild about that question. I'm certainly going to say, this is good. Number 9, which of the following statements is correct? Sure, that's true. Sure, that's true. That's false. So first of all, I'll cross out anything that's got that. 1 and 3 only is 2 true. Spectroscopes have shifted the background. I don't think spectroscopes shift. They measure radiation. I don't think they actually shift it. Let me just see. I'm checking my answer key because I think that's kind of a weirdly... Yeah, that's not true. Spectroscopes measure. They don't change radiation. They don't give off radiation. So the correct answer is A. Stars moving towards you, wavelengths become compressed. This also explains why the sound of a car or a car's horn changes as it drives towards you and passes you. If a star is moving away from you, wavelengths get longer. We call that redshift. By the way, we call the other one blue shift, but redshift is really the one I want you to know about because that's what seems to be happening to the universe. Some more vocabulary. Inside a galaxy, a huge group of blank, and you know what? Dust would be one word. Gas would be another word. No. And you know what? Galaxies also have stars. Sure. Galaxy is a huge group of dust, gas, and stars. Stuff. What I really want you to know is what holds galaxies together. Begins with a G.
Gravity.
And this is where I mentioned at the end of last day, Aiden and Riley, I have a video for you later on. Remind me, it's what you would see if you dove into a black hole, because you asked about black holes, yeah? I'll try and fit it in class today, or I might not get to it till Tuesday. We think at the center of each galaxy is a supermassive black hole. That's what's gravity. That's the gravity that's holding everything there.
What happens if you go in?
Patience and watch the video. Then I get to it. There might be as many as several. This is already out of date. We now think there's about 100 billion galaxies. And each galaxy might contain more than a... This is already out of date. We think most galaxies average around 100 billion stars.
Yeah.
And we're already at numbers I can't, Kyle, wrap my brain around. What's the name for a dense cloud-like collection of gas and dust in space? I put a star next to it, means it's important. It's a nebula. Mitra, was your hand up? I didn't see it, sorry. And in fact, nebula, these are star nurseries. This is where stars are born. Stars form as clouds of dust and gas, and they gradually coalesce and compress upon each other. And if there's enough of it and enough pressure, all that fusion and heat that we talked about last day starts. If you could look down at what galaxy looks like a pinwheel when you look at it from above, what type? Spiral? You need to know what a spiral galaxy looks like, so I'll put a star next to there. You need to know what we are a part of. The sun is a part of which galaxy? The Milky Way galaxy. And what type of galaxy is the Milky Way galaxy? The one that has cereal and milk? Sadly, no. I figured that out. Help me out. What do we got? Spiral. What type of galaxy has the shape of a flat circle? Elliptical. You need to know that. And then galaxies that don't have any type of a regular shape are called irregular. Pretty creative, I know. What and what are the building blocks of stars? Yeah? Gas and dust. What do we call groups of stars within galaxies? Star clusters. Hey, the nice thing, Matteo, you'll notice, in physics, we know how to name things. We didn't give these some silly Latin name like endoplasmic reticulum or Golgi, but some of the stuff in the cell drives me crazy. Physics, we know how to name things. Got a group of stars, they're clustered together, let's call them a star cluster. Star clusters, or no, never mind. We had a special subtype. We called these globular. Now, I am going to say you need to know this, number 9, number 8, and number 7. Globular, meh. And then we have what we call open clusters. Yeah, I'll say, you need to know those two. Those are clusters of up to a few thousand stars that are roughly the same age. Globular clusters are collections of 100,000 to about 1 million or so stars. What is a galaxy? Stars, dust, and gas held together by?
By gravity. Yeah. Okay.
What are the 3 basic type or shapes of galaxies?
Elliptical, spiral, and I know this one, but I can't remember it.
There is a reason you can't, because it's not special. Irregular.
It was on the tip of my tongue.
Spit it out. What type of galaxy is the Milky Way?
Our galaxy.
I know it's ours. What type? Yeah, it's a lovely spiral. Oh, spiral. Okay. Which type contains the oldest stars in the universe? What is found in an irregular galaxy?
Dust. Gas.
You know what, man? Yeah. You know what? I got to look this one up. My answer key doesn't have it. I forgot to write it down, and I'm blanking out. So, let's pause the video, Mr. Dueck. So, Mitra, you were right. Old stars and newly forming stars. What percentage of the galaxies are there that are elliptical, approximately? Remember what we said? Actually, I said, so over 50%. What are the 2 types of star clusters? Globular and open. How do they differ? Globular, shaped like a globe, more stars. What did I say in the last one here? 100,000 to 1 million stars, right? Open, around 10,000 or so stars. I think that's what I said. Few thousand stars. Shapes, that I'm going to let you do. I'm not going to mark that. You have plenty of pictures and you get to draw a little bit in color. So we're going to jump to the very, very end here. I think number 1 is A in elliptic. Let's try that again, Mr. Dueck. An elliptical galaxy is round or all the way flattened out to a cigar. A galaxy, enormous collection, you know what? G. Oh, G for galaxy, that works well. Irregular galaxy, well, it's not shaped like a sphere or a pinwheel, it's shaped like a weird thing. Nebula, cloud of gas or dust in space. Spiral galaxy, looks somewhat like a pinwheel. Star clusters, a collection of a few thousand or a few million stars. Sorry, a few 100,000 stars. By the way, you know what I forgot to do? If you want to, on 2 pages ago, you need to know that, 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 you need to know that. Every question here, to me, is fair game. I like each question, I like each question, I like each question. Number 7, Sun is a part of a spiral galaxy. Which one holds the oldest stars in the universe? Ellipticals. What holds globular clusters of stars together? Also gravity, because stars have gravity too. So they're held together. The same way all of our planets are held in place by gravity from the sun. 10, B, a few thousand for an open cluster. Astronomers think that over half of all galaxies are elliptical. What's true of the Milky Way? Does not have the shape of a flattened circle. From above, it does look like a pinwheel. From the side, it looks like a plate with a ball in the center. That's true. Does it have lots of young stars? Spirals are younger galaxies. So you know what? I think the answer here is C. Okay. Okay. How'd that go? Thumbs up, thumbs down? Okay. If you have that done, I'm not going to say put a score at the top. I'm just going to see and look and see if you corrected it. If you have it done, you can hand it in. And now we're going to talk about what we're going to do today. So what we're going to spend time doing today is learning how it is that they classify stars. How is it, because we don't go out to them, how are we able to say, hey, I know that's a red giant. Hey, I know, even though that's billions and billions and billions of kilometers away, that's a blue dwarf. Hey, I know, how is it that we do that? And it turns out 2 scientists, Hertzsprung and Russell, studied a whole bunch of stars. Aiden's going to put his phone away before I freak out. And they made a chart. And that chart is the picture you have on page 374. So make sure you're on page 374. Okay? Here is how you classify stars. What we do is we graph their luminosity and their temperature. And then looking at where it appears on the graph, we then compare that with where it appears in the diagram. So can you, looking at the handout that I gave you, this one here, on page 3, there's a piece of graph paper. I'm going to suggest if you carefully tear it off, it's going to be easier to have it in front of you, and then restaple it on when you're done. Okay? So, this handout here, rip off the last page. So you have the graph in front of you. You be okay? Okay? Nicole, this handout here, rip off the last page, so you have the graph in front of you. And I'd like you guys to keep the graph in front of you right now, and I'm going to classify a mystery star. Ready? So here is the data. I've been observing a star through a telescope, and I'm not going to tell you how we get these measurements. That's too complicated. But I've calculated, based on observations, that it has a temperature of 28,000 degrees and a luminosity of 0.0001. Okay? It's got a temperature of that and a luminosity of that. Let's remember that. So you're going to remember the temperature for me, 28,000 degrees, and you're going to remember the luminosity, 0.0001. What I'm going to do is I'm going to go to the graph. What was the temperature? 28,000. Temperature is along the bottom. 28,000 will be about there-ish. Closer to 25 than to 45. About there. What was the luminosity? Sorry? 0.00, how many zeros? 3? Okay. My mystery star would appear there on the graph. Don't write this down yet, just watch. Aiden, just watch. Okay. My mystery star would appear there. What kind of a star is it? Now I go look at my Hertzsprung diagram. It appeared right there on my graph. What stars are in this area on the diagram? I would say this is a white dwarf, and that's how I would classify it. Okay, that's why you need the diagram and the graph paper in front of you, and trying to do them both on the same sheet just doesn't work. So you have the textbook. Let me do another one. The second star that I had, this time, Lena, you're going to remember the temperature, and Kiana, you're going to remember the luminosity. So here's my second mystery star. Oh, where am I? Star number 2. So, Lena, remember 4,000. Kiana, remember 0.001, 2 zeros and a 1. Okay, you can remember that? You remember that? So if I was going to graph it, what was the temperature, Lena? 4,000, which would be right around here. And what was the luminosity? 2 zeros and a 1, which would be right about, you know what? It'd be around there-ish. Then I would go to my Hertzsprung diagram and I would say, oh, what kind of a star is that? Because that's the area that I graphed it. Is it a low mass star, an intermediate mass star, or a massive star? Low mass. And you know what? Probably a red dwarf. Does that make sense? So on the lab that I've given you, don't graph these 2 mystery stars because I made them up. They're not real. But what I did is I found data, both from the textbook and online, of a bunch of stars, 13 in total. What you want to do is you want to graph these on the graph paper. And what I would do is put a dot and then put a 1 next to the dot. That's Altair. Put a dot, put a 2 next to the dot. That's Antares. You can, that way, you can try writing the names, but it's going to be too cluttered. I would just put the number next to it. So let's do number 1 together. So Aiden, you're going to remember, because I have to scroll to a different page, you're going to remember the temperature. Amelia, you're going to remember the luminosity. So you're going to remember 8,000, you remember 11. Let's all go to the graph paper. What was the temperature, Aiden?
8,000.
Which would be just to the left of 7,500. What was the luminosity? 11, which is slightly above 10. Let's all of us on our graph paper put a big dot right there, and that's star number 1. What kind of a star is that? Well, that's right around, where? Here. Well, let me look. Kyle, what? I probably think it's a supergiant. Now, so in the lab, in the first column, classification, what's the next column say? Color. So remember where it was on the graph? Also on the Hertzsprung-Russell diagram, at the bottom it also has color. You know what? Halfway between blue and red, what color would you say based on the pictures here? Begins with letter O. Probably orange. Orange if you feel Québécois. Okay. Kiana, does that make sense? How you're going to do that? You're going to plot it on the graph. It's a weird graph. You have to look at the numbers very carefully. In fact, some of the questions I'm asking you is, how is the x-axis different from a typical graph? You know what? Usually graphs get bigger going this way. This graph gets smaller going this way, and it doesn't go up by even chunks. We have to kind of modify it because there's such a wide range in stars. If we didn't do that, then, Nicole, we couldn't get this all on one piece of paper. So this is what you're going to try and finish in class today for sure. This Hertzsprung-Russell, so you're going to plot and categorize these 13 stars, and then you're going to answer question 1, question 2, question 3, question 4, question 5, and question 5. Now, some of these answers also appear on page 374 and 375, so you're asking, what was it asking? Some of those answers appear there, or I'll talk about them next class. You got a question?
Do you want us to write the name of the stars?
I think if you write the name of the star trying to fit 13 on here, it's going to get cluttered. I would suggest put the number of the star that I have next to it in the chart. In other words, when you do the second star, call that star 2. You can write. Last year I had kids write the name, it just got cluttered, and you couldn't tell because sometimes the name was halfway between 2 dots. Which one does it belong? You can put a number nice and close to the dot. Okay, that's assignment number 1. So take a look at this handout. If you guys stay looking at the front of this handout, I'm actually going to read the instructions on the back. Here's what it says. There are instructions on the back, but stay on the front. It says, complete the flow chart on the front side about the life cycle of stars. You're going to be using page 370 to 372. In fact, in particular, you're going to be using this picture here. Remember, this picture had low mass stars, intermediate mass stars, and high mass stars. It has 3 rungs. You'll notice what I've given you in your little flow chart has, once you get to here, 1, 2, 3 rungs. So low mass stars, intermediate mass stars, and high mass stars. What we're going to talk about is what each stage goes to. You're going to have to get this from the textbook, and I'll help you with it if you're stuck. So it says on the back, start by filling in the stage boxes using these words below. You'll use every one of these words. You can refer to page 370 to 372 to help you. You can also Google on your smartphone if you think that'll help as well. You're going to use all the words. Some of the words might get used more than once because maybe more than one type of star ends up as a white dwarf. I don't know. Then draw sketches of each of the different types of stars in the boxes. You can use pencil crayons, I'll bring them out, or you can use a pencil. Remember to make small stars smaller and big stars bigger. Some of these stars you might not have a good idea of what they look like. You can either use your imagination or do a Google search so you can find a good image. And then make notes about what makes each star unique. You should talk about their relative size, their temperature, hot, cold, or in between, when or why a star enters that stage, or why it becomes one type of star versus another, and then indicate which stage allows the formation of the heavier elements. All of that is contained starting here on page 370, where it talks about low mass stars, intermediate mass stars. By the way, if you're wondering what goes in the very, very first stage, it goes nebula, protostar, and then you break up. So here's your nebula, protostar, and then that breaks up into the 3 different types. Does that make sense? You have to do some reading on your own and some work. This is different from the previous units, and I'll help you as we go. There is 20 minutes left. So you got the rest of class. Hertzsprung-Russell diagram is your first priority, as well as, if you can, oh no, did I give you any homework last day? Oh yeah, I gave you this. See if you can get this done too, but I'll give you some time next class too. Questions?